I'm Vitalii Vitko from St. Petersburg, Electrotechnical University, LT, and I welcome all participants of the Trends in Magnetism Conference. The topic of my talk is investigation of microwave bistability in spin-wave active ring resonator. Before I begin my presentation, I would like to thank the conference organizers. Also, I'd like to acknowledge the role of Boris Antonovich Kalenikov's, who has been the inspiration and driving force behind the research. To our deep regret, Professor Kalenikov's left us last year. Allow me to make a brief introduction into the field of spin-wave nonlinear dynamics. It is well known that depends on the film configuration, there are three kinds of spin wave. The surface spin waves, which corresponds to an in-plane wave propagation perpendicular to the magnetic field. The backward volume spin waves propagates also in plane, but co-directed with the magnetic field. And it leads the forward volume spin waves. It is the waves propagates in normal magnetized ferromagnetic films. The surface spin waves have a normal dispersion, which corresponds with a negative dispersion coefficient. The increase in the amplitude of spin waves produces a downshift of the dispersion curve, which corresponds with a negative nonlinear coefficient. That's why this kind of spin wave have repulsive nonlinearity. The backward volume spin wave have attractive nonlinearity due to the positive dispersion coefficient and negative nonlinear coefficient. The forward volume spin wave had negative dispersion coefficient and positive nonlinear coefficient, which correspond with a positive nonlinear frequency shift. In our work, we focused only on investigation of forward volume spin waves due to a higher value of the nonlinear coefficient. There is the classical configuration of the active ring resonator. It contains a microwave amplifier, a delay line, and two-direction couplers. In our case, the yttrium iron garnet film with two microstrip antennas is used as a spin wave delay line. The distinguished feature of the spin waves is a relatively small wave velocity, which is appeared as a large delay time, about 100 nanoseconds at lengths about several millimeters. That's why the delay time in other elements of the active ring resonator can be neglected. Herewith, the resonant condition for the ring is the equality of the phase to 2p. The phase accumulated in the ring determined by the wave number of the spin waves and the distance between the antennas. The spin waves has a highly dispersive characteristic, and the losses of such spin wave delay line will have dependence on frequency. The length of the active ring resonator circuit is much longer than the wavelengths of the operating wave. Therefore, the output signal have an multi-resonant spectra. Moreover, the resonant wave numbers is defined by 2pm divided by d. The frequency range of the spin waves can be tuned by the change of the external magnetic field. So the spectra of the spin wave active ring resonator also can be tuned in a higher frequency range. I want to underline that the spin waves active ring resonator have two distinguished features. The first is the spin wave demonstrate different dispersion and nonlinear properties depending on the field film configuration. And the second is that the spin wave active ring resonator setup allows one to control the losses and observe various nonlinear effects as well as the bistability phenomena. Due to this feature, the active ring resonator can be used as a high Q tunable comb filter in case of following condition: the amplifier does not compensate the losses. From the other side, in case of total compensation of losses, the active ring resonator works as self-generator, and it can operate in monochromatic or solitone regimes. However, close to the self-generation threshold, at the resonant frequencies, the amplitude of the signal increases significantly. In such condition, the bistability phenomena manifested itself. And despite of this effect is well known in optics, there are no theoretical approach to explain it in spin wave active ring resonators. Besides, nobody have defined yet the bistability threshold. The purpose of current work is to investigate the microwave bistability in active ring resonators on forward volume spin waves. In order to achieve this purpose, we develop a theory of nonlinear transfer function formation in spin wave active ring resonator. The monochromatic signal input in the ring in following form through the directional coupler then transforms into a spin wave and propagate through the spin wave delay line. Then it's come back in the ring as a microwave signal, and part of the drop out from the ring by the output directional coupler. Other part of signal continues the propagation in the circuit and pass through the amplifier. Amplifier regenerates the signal till the defined level below the self-generation. So the signal circulation in the ring can be described by the wave factor, where kappa 1 and kappa 2 are power coupling coefficients, and A is the loss factor of the ring. For the case of linear damping, the loss factor is defined as follows. Following our consideration, the signal applies to the input of the ring in continuous mode. That's why the amplitude of the circulation signal is described as the infinite sum of the circulated waves that are not get out from the ring, and the amplitude of the output signal corresponds as the sum of the signal which get out from the ring, and describes as follows. The power transmission coefficient in this case can be derived in the following form. One can see the resonant condition in case of phase shift in the ring is equal to P. Here is the wave number have to be obtained from the nonlinear spin wave dispersion law. Let me remind the mechanism of the nonlinearity of the spin waves. The total magnetization M is the sum of the static magnetization M0 and the dynamic magnetization M, which corresponds to the dimensionless amplitude. Due to conservation of the absolute value of the vector M, an increase in spin wave amplitude leads to a decrease in the static magnetization. It's shown by red lines on the figure. In case of forward volume spin waves, it leads in increase in the angular frequency of the ferromagnetic resonance omega h and in decrease in the omega m. In order to obtain the dispersion characteristic, both omegas are substituted in the dispersion law. That's why one can see that increase in the amplitude of the spin waves produce upward shift of the dispersion curve and corresponds to the positive nonlinear frequency shift. At the same time, the circulated amplitude at the resonant wave numbers is much higher than at other wave numbers. In order to consider the increase of the amplitude of the circulating signal close to the resonant frequencies, following denotation should be done. Therefore, the dispersion characteristic has kinks, and the nonlinear transfer function, HP, is obtained by the substitution of the roots of the dispersion equation into the power transmission function. One can see that it corresponds to not only the nonlinear frequency shift, but also distortion of the transmission characteristic, which is manifestation of the bistability phenomenon. Using our approach, the detailed investigation of the bistability behavior in active ring resonator on forward volume spin waves is carried out. For its demonstrative description, we introduce the nonlinear dispersion surface and nonlinear response surface. The results of the numerical simulation of this surface present here. Following parameters was used for the numerical simulation. This surface instructively demonstrates the evolution of the nonlinear dispersion and transmission characteristic due to increase in the normalized amplitude of the spin waves. Further consideration will be given to determine the threshold value of the amplitude. Consider transformation of the dispersion characteristic and transmission coefficient that rise with the increase of amplitude U. Here you can see the dispersion and transmission characteristic in linear regime. The linear transmission characteristic has Lorentzian shape. The increase of the amplitude till the threshold value manifests itself as the appearance of the kink on the dispersion and transmission characteristics. Therefore, in order to obtain the threshold amplitude, we use the derivation of the dispersion law instead of the derivation of the transmission characteristic. Using our approach, we obtain the following equation for the threshold amplitude, taking into account linear losses. The dispersion relation and the frequency response become multivalued above the threshold. The frequency region of the bistable behavior is bounded by the extremums of orange and blue circles. Here you can see the frequency range of the bistable region. Further increase in the amplitude leads to enhance the bistability region. I would like to underline that the bistability threshold is determined by the gain coefficient, and it is natural that bistability enhancement is limited by the nonlinear damping. During our investigation, we predict one more distinguished feature of the bistability regime of the spin wave active resonator. The transition to bistability regime is determined by the gain coefficient as well as by the input amplitude. Further consideration will be given while the input amplitude is fixed. Green lines, like in previous case, calculated for the low amplitude represented the linear regime. An increase in the gain coefficient causes a rise of the transition coefficient and a nonlinear frequency shift. The bistability threshold manifested itself as appearance of the kinks, like in previous time. So, using our approach, we describe the following form of the threshold. The dispersion relation and the frequency response become multivalued. Further increase in the gain coefficient leads in enhancement of the bistability region. Note here that the gain coefficient is limited by the self-oscillation threshold. Let me summarize now. We develop a new theoretical approach describes the nonlinear dispersion and transmission characteristic. During our investigation, we predict that increase in the circulation amplitude of the resonant modes produce a local nonlinear frequency shift that leads to a bistability behavior. Proposed original approach is used to derive the bistability threshold for the input amplitude as well as the gain coefficient. And finally, represents that the dynamic range of the bistable behavior is a function of the gain coefficient and input amplitude. Therefore, the dynamic range begins from the bistability threshold values for the gain and for the amplitude and is limited by the self-generation and by the nonlinear damping, respectively. Thank you for your attention.